to some of the ones we did last week, and it is an asynchronous counter. And what makes it asynchronous?
They're not all dependent on the same clock cycle?
Yeah, they're not all dependent on the same clock cycle. So if you look at the various different flip-flops, only the first one has the input of the clock, and all the others have the input of the output of the flip-flop before it. And what kind of flip-flops are these? J and K. And what are the inputs into J and K? High. So that means that I could just as easily have drawn this with what kind of flip-flop?
I'm assuming a D flip-flop.
D wouldn't quite work. I'd have to put some other gates in to do a D. What does a JK flip-flop if both J and K are high?
Go back to 0?
Toggles.
Oh, okay.
So it could have been a
T flip-flop.
T flip-flop, right. So J is set, so J makes it 1, K makes it 0, or the other way around, I can never remember. If they're both 0, it's no change, but if they're both 1, then it's a toggle. So this means that every time it'll toggle whatever it was before if you're on the positive edge of a clock cycle. And how do you determine if you're on the positive edge of a clock cycle?
When it switches from low to high?
When your clock signal switches from low to high. Okay, so timing diagram appears to be as if this is on the negative edge. Yeah, so I'm going to, well, I'll do it. I'm worried because now it's not going to match my answer, but my answer that I have has it being at a negative edge. So where are the positive edges of the clock for Q 0? So for the first flip-flop, where do I have a positive edge?
Anytime it goes from 0 to 1?
Anytime it goes from 0 to 1. So it'll be all of these. Okay, so now, is there any reason why that first flip-flop would not toggle when going from, when the clock goes from 0 to 1?
What do you mean by that?
Is it going to toggle at every one of these vertical lines? Is it going to toggle?
Yes.
Yeah. Boy, I cannot draw straight. And then now you see that this that we just drew that is now the input into the clock for the second flip-flop. And so the second flip-flop is looking at this output as its clock. And so it is also positive edge triggered. So it is going to toggle every time this one had a positive edge. Okay, and now y'all see if you can fill in the signals for Q2 and Q3 on your own, and I'll do it up here as well, and then you can check yours after you have done it. Always pay attention. You know, they could throw one at you where perhaps it's not exactly the same on each one, but it is on this one. It's always the output from the previous flip-flop is the input into the next one. One of these is the one that I have my solutions on. Flip through your packet if you pick one up and just make sure it doesn't have, like, it has a big, you'll recognize it if it has something on there that doesn't belong. I'm going to check my office. made a separate solutions file that was lost it. We'll have to do that. Okay. All right, so moving on. What is a register? And explain the difference between serial and parallel data. So have y'all talked about registers at all?
I believe we have.
Okay. Do you know what they are? Okay, so they're made up of flip-flops. And what is the definition of a flip-flop, or what when we get away from combinational circuits and start doing sequential circuits, what is it we say that the flip-flops have that our other circuits didn't used to have? Memory. And so what a register is a register is going to be a series of flip-flops, and that you're using them. They're usually D flip-flops because those work well, and you're using them to hold some amount of data for a short amount of time. And when you get more into computer architecture, you'll see that that's literally what a register is when you start talking about a register. So what is a register? And we get had a nice formal definition. Okay. So a register is a collection of flip-flops or latches that's used to store a binary number, several bits. And so you would have, like, if you had 4 flip-flops, you could store a 4-bit number. In essence, it's a one-word memory circuit, so a word is defined in a different way depending on your architecture as to how many bits it is. And so it has, rather than having a memory of 1 bit, it has a memory of a certain number of bits. Now, a shift register is a register that holds the memory, but it also has the ability to move the bits around from place to place. So that is the definition of a register. Good, nice definition. Now, what is the difference between serial and parallel data? And you want to make a guess?
Does serial mean that it has to be sequential in order for information to change, whereas parallel is simultaneous?
Yeah, serial, you do things one at a time, and parallel, you do multiple at once. So when you talk about parallel processing, it means that you processing more than one thing at the same time. Serial processing means you're processing one thing right after the other. So this is an analogy for a shift register. And so we have items coming in and items going out. And you want to look at that diagram and decide, is it parallel in or parallel out? Or is it serial in and serial out? So which is it, parallel in or serial in, or is it parallel out, or is it serial out? So here's our 2-bit register.
Would be serial in and parallel out.
Yeah, it'd be serial in and parallel out. And how did you come up with that?
It looks like the blocks are coming in one at a time and then clearing out at the same time.
Yeah. Serial in and parallel out. And when you load things or retrieve things by parallel, you have parallel wires, getting the data all at the same time or adding the data. All right, so how about this one? Parallel in or serial in and parallel out or serial out.
Parallel and serial out.
Parallel in because they're both coming in at once, and serial out because they're going out one at a time. And then our last one. How about you?
Serial in, serial out.
Serial in, serial out. Any of you live in an apartment?
I do.
Find when I was apartment living, cereal was a main food source. It's easy, tastes good, it's quick, it's filling.
And Pop-Tarts.
Yeah, Pop-Tarts. All right, so now let's take a look at our first problem. Well, I guess the timing chart was a problem, but okay, using a 4-bit synchronous counter with parallel load, see below for inputs and outputs, and a minimum number of additional gates is needed to construct a counter that counts from 0101 through 1001. Repeat for a count from 0101 through 1101. So one thing that you can expect is if they tell you it's a counter, then it is a counter and it works and it counts. They might tell you it's an up counter or a down counter. Here it just says counter, so we'll assume an up counter. And that it's synchronous, which means on each clock cycle it will count unless you tell it to load. And so what that means is whatever value it's starting on, like let's say it starts on 010011, then on the next clock cycle, it'll count to 0100, and then on the next clock cycle, 0101, 0110, 0111, 1000, 1001, 1010, 1100, 1101, 1110, 1111, and then it will automatically go back to 000. You don't have to tell it to do that. It's just going to go back 0001, 0010, and then it would be back where it started. So if they tell you it's a counter, you can expect that it counts with the number of bits that it tells you that it has. Now, one thing you have to be careful with is when you look at your outputs, this is the most significant bit, and this is the least significant bit. So when I'm looking at my numbers over here, this is Q3, and this is Q0. Now, whenever the load gets a signal to load, instead of counting, it'll load whatever value is on these D inputs. So, for this counter, we will put 1 on the enable because we want it to be enabled. The reason you might not put a 1 on the enable is if you're chaining these together to make a bigger than 4-bit. If you had bigger than 4-bit, what you would have on the enable would be the output carry of the one before. So this, if I was chaining these together to make an 8-bit, which is not part of this problem, but just in case you wanted to know, the way you do that is you make the carry on this one enable the second one, and then that makes it have the higher order bits. But that's not what we're having to do on this one. I was just telling you why they were there. Okay, so we want it to start at a certain value. So I'm going to have the clock right here. And we want it to start at 0101. So this is D0, D1, D2, and D3. So I want to put those on these values over here. So D0, D3 will be 0, D2 is 1, D1 is 0, and D0 is 1. Notice this 1010 looks opposite from the way we read it. It's like up to down is backwards. So we want it to count starting from that number until it gets to 1001. So we would assume that at some point we tell it to load. So we told it to load, but we're not putting anything on that right now. Just say that that happened, and it's going to count. And we want it to count until it gets to 1001, and then we want it to go back to 0101. So the way we do that is we look at this number 1001, that's Q3, Q2, Q1, and Q0. So when I get those numbers as my outputs, so I get 1001, when I get those, that's when I want to tell it to stop. And so what I can do to make that happen is I can AND together those gates and then make that be the input to the load. Because the first time both of those are 1 is when I've gotten to 1001, and when I attach that to the load, then that will tell it to reload these numbers and it'll start over. Now I could have, if I wanted to, also ANDed together the knots of these ones that were 0. Most of the time you would not have to do that. The only time you might have to do that is if you have a sequence that wraps around, like it starts at, like the way I counted the first time over here on the side. And then you'd have to look and see, might you have to catch those zeros as well. But I know I don't need to in this case, because the first time these were both 1 was with the time that I needed it to start counting. Okay, then it says to repeat for a count from 0101 through 1101. Okay, so I'm going to erase what I have here. And y'all go ahead and write down, count up from 100 to 1101. So just practice your binary numbers, make sure you can do that. So we're counting up to this number. So in case you never really counted in binary, what you do is, I'm going to add 1 to the end. Okay, so now if I want to add 1 again, that means I have to add 1 to the place before and then make that 0. And then I can add a 1 again. And you just keep moving along like that, adding 1. So you get to 1101. Okay, so how are we going to get this one to stop at 1101?
You do the same thing, you put a NOT gate on
On Q1 for 1101?
Q1. Oh, then one
Okay, so we could do that. So, but remember, these are in reverse order. So this is Q0, Q1, Q2, and Q3. So we can AND together. So you're saying put a NOT gate on Q2 or Q1.
Q2.
Yeah, Q1, Q2. Yeah, no, Q2 is 1,
So the number I'm trying to reach is 1101. This is Q0. This is Q1. This is Q2. This is Q3.
and D3 correlates to Q3, right?
D3 is the input. The D's are the inputs. These are the outputs. So we're looking at the outputs. We want it to stop when the output gets to 1, 1, 0, 1.
Would you AND Q0, or Q0, Q2, and Q3?
That is what I would do. Because the first time in my counting sequence that these are all 1s is when I reach this number. And you have that go into the load.
So
just says Q1's not part of the gate. It just assumes it's a gate.
Well, we don't need it to be one, it's an AND gate. And so if we wanted to include it, we would have to put a NOT gate on it and AND it in.
And when load is 1, it resets or stops.
And when load is 1, it loads these up again to restart counting. And you can put that NOT gate in there. And that doesn't change anything. It's just if you don't have to, you don't have to. Sometimes there can be like a really simple way, depending on what your count sequence is, because if your count sequence is to go from, I don't know, sometimes you might be able to get away with fewer wires, but it's usually easiest just to AND together the ones, and that usually will work. If it does wrap around, you might need to AND in the zeros, the knots as well for the zeros. Okay, any questions on that one?
So in the logic diagram for this circuit, how would enable be accounted for in the logic diagram?
It'd be Are you talking about for a circuit or?
Yeah, for the logic gates, what would enable?
To the VCC to high.
Oh no, I guess what I mean is in the gate diagram, where would enable tie in to actually allowing all of this to happen? What would how would that be put into the diagram?
I see. Hold on, I'll show you. So the way with this particular counter, the way it was done was by having the enable, a wire for enable, so that'd be a switch going into a T flip-flop. And so if enable is 1, it's going to toggle because counters toggle. That's how they work, is they toggle. But if enable is 0 for a T flip-flop, that means don't change. And then from here on out, so if the first flip-flop is 0, then it's not going to change. And so if it doesn't change and the enable is 0, then you're going to have 0 going into the second flip-flop as well. And then from then on, you'd have 0 going into all the T flip-flops so that they would just stay where they were. So
So the enable really only controls the initial one, but it's kind of layered on top of that one?
Right,
Okay.
right. And that is built into why it works to be able to chain two of them together, because when you chain two of them together, when you count like beyond the first 4 bits, so after you get to, so you have your second flip-flop, which has been not enabled, so it's just been sitting there at 0, 0, 0, and your first flip-flop has been counting, it was at 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and then it gets to, didn't leave myself enough room. Zero, 1, 1, 1, 1, 0, 1. No, that's not what I meant. I'm the wrong. I meant this. Okay, so when you get to this stage, the way the output carry works is it's the AND of all of these. So the AND of all of these enables this counter over here to start counting. And so then it will count to 1. These will roll over to 0. And then this one's not enabled anymore. And so this one will start counting again until it gets up to the time that it's ready to get to where it needs to enable the second one again to count. And so once these are all 1s again, it enables this one to count up to the next one. And this one rolls over, and then this one's not enabled anymore. So that's how the two get strung together. All right. All right, so let's talk about a Johnson counter and a ring counter. So a counter just means it follows some sequence. So it doesn't have to count up or count down. It just follows some sequence. And the way a Johnson counter works is like this. So let's say I have 1, 0, 1, 0. So the way a Johnson counter works is this last bit flips and comes around to the front, and the other bits slide down. And so the last bit flips and comes to the front, and the other bits slide down. So these 3 became these 3 right here. And then the front 3 here became the last 3 here. So we had 1, 0, 1, 0. The next one we got was 1, 1, 0, 1. The next one we'll get will be 0, 1, 1, 0. And then this 0 will come in front as a 1. And then I'll have 0, 1, 1. And then this 1 will come in front as a 0. And I get 1, 0, 1. And this 1 comes in front as a 0, and I get 0, 1, 0. And this 0 comes in front as a 1, and I get 0, 0, 1. 1 comes in front as a 0, and I get 1, 0, 0, and the 0 comes in front as a 1, I get 1, 0, 1, 0, and I'm back where I started. How many is that? Counting the repeat, so eight different states, right? 8 different states. And how many bits did I have? 4 bits, 8 states. Do you think it's possible that I would ever have fewer states?
That's good.
If you had a load that intervened somewhere in between?
Yeah, I can't think of any way to do it without, maybe if I had an odd number, like if I had 1, 0, 1, so the max number of states I could have would be 6. Let's see, and I would get 0, 1, 0, and then I'd get 1, 0, 1. Yeah. So with an odd number of bits, I would only have 3 states instead of 6. But if I had an even number of bits, I think you'd always have that number. Okay, but this question says for a 4-bit Johnson counter, starting from an initial state of 0, 1, 0, 0, list the sequence of states of the 4 flip-flops after each shift. How long is the sequence until it repeats? So 0, 1, 0, 0. So y'all see if y'all can write it. So 0, 1, 0, 0. So see if you can write it, and let me know if you need help. If you were following along but then forgot what I said or whatever. When you're done, you can check. I wrote them up here. You can check me, see if I have it right. Okay. And it was 8, and the sequence should have been 8. Now, 0, 1, 0, 1, is that the one I just did as my example? No, I did 1, 0, 1, 0. So, okay, so now y'all do 0, 1, 0, 1. And again, you should have gotten 8 states. Okay. Any questions on that?
I guess like the biggest gap that I have is like what is this useful for? Because I can follow the pattern that you gave me, right? But whenever it comes to telling us like, oh, use a Johnson counter for this. Like, how would I be able to interpret that in order to apply?
Well, I'm glad you asked, because
Or if like the option was given to us to be able to use a specific counter, how would we know like, oh, we need a Johnson counter for this, or we need one of those D flip-flop counters?
you're almost always going to want to have like an up counter or a down counter. I mean, the Johnson counter and the ring counter would have special purposes. A ring counter makes perfect sense because it just continues, like it just repeats. I thought I had more on here than I have. Let's see. Type of synchronous counter implemented. It's used in applications where the number of states is higher than the number of flip-flops. You could also use an up counter for that. It has a distinguishing feature of self-decodability, which basically means you can use it to check itself. That just does not tell me. See if by any chance I still have that website open, because it was good. Applications. It's used as a synchronous decade counter or a divider circuit. It's used in hardware logic design to create complicated finite state machines, such as in a field programmable gate array design. So in the class I dropped this semester, that's where you do more work with finite state machines. It could be used as a three-phase square wave generator. It is used to divide the frequency of the clock signal by varying their feedback. Okay, so those are some applications for it. I don't know. How would you know to use one at this stage? You wouldn't. I mean, anything you're going to use is just going to be a regular counter. I am interested to see it say used to divide the frequency of a clock signal, because there is an application where you won't do it this semester, but one of the professors who teaches this class does divide the clock signal, and we use a regular counter, and now I'm wondering if a Johnson counter would be better for that. Okay, so a ring counter is like a Johnson counter, but it's easier because it doesn't flip the bit as it comes around. So it just keeps that same bit. So here we have one that is a 4-bit ring counter starting at 1001, and we want to count until we get back to where we start. So the last bit just comes around to the front and does not flip. So this would be useful if you needed to have like exactly in states for your finite state machine. But, you haven't done finite state machines yet. You're getting there. So this will make more sense when you get there. So when you talk, you'll talk about the number of states that you need. And in general, if I had in bits here, so however many I had in bits, how long would the sequence be before I repeated?
The last one should be 100.
It should have been 100. Yep. So this one had 4 states. If I had in bits, how many states would I have? How long would it take before we got back to where we started? It's just going to be however many bits you have, because it just has to. This one just has to migrate all the way to the end and come back around. So end states.
You probably said this. If the Johnson is always going to be 8 states.
Or less. 8 is the maximum. And for a ring, n is the it's n, the number of bits.
Yeah.
So 2n is the maximum for Johnson. So Johnson 2n is the max, and for a ring, n is the max. And I believe for a Johnson, I think it would always be 2n if you had an even number of bits. I'm not sure. You could have less if you had an odd number of bits. Okay, so now we're going to do some Verilog with a multiplexer. Okay, so what does a multiplexer do?
Gives you a certain output. I assume. Something else. So it gives you like different option.
So in this instance, if V1, V0 is 0, 0, then our output would be C and D.
So it's just conditional.
Yes, this is just conditional. Not, I can't draw an and symbol, so you just have to pretend that's an and. If it's 0, 1, it is C or D. If it is 1, 0, E and D,
Should C and D.
C and E. 1, 0. Do I have something wrong? Right, and E.
Mhm.
I was just gonna do E first. It's an and. That's an and. See. And 1 is just E. So module mux C D E V0 V1 and F input C D E V0 V1 output F and we'll have an always block. So always at, and then you have your sensitivity list. And so you want it to change whenever any of the, you want it to run this always block whenever any of the things inside this sensitivity list changes. So anytime V0, V1, C, D, or E changes, we'll want to do our always block. And now, if I had more than one statement in here, I'd have a begin and an end, but I'm only going to have one statement. I'm going to have a case statement. And I'm going to have case, and then I put in curly brackets V1 comma V0. And what that does is that makes a single binary number out of V1 and V0. And then I'm going to list my 4 possible cases. So the 2 tells me it's a 2-bit number, and then I have the apostrophe. The B tells me it's binary. So case 2B00. So if I have 00, then I want F equals, what do we say, C and D. And again, if I had more than one line here with each of these cases, then I would have a begin and an end, but I don't. So 2B01, F equals C or D. To B10, F equals C and E. Apologize for my hands. And 2B11, F equals E. And then end case. And then I didn't have a begin on my always block, so I don't need to end the always block. And I think that's the end of the module, so I can end module. So this was just a quick example to show you how you can do a multiplexer in Verilog, and how to concatenate two variables to make them into a binary number, a 2-bit binary number. So, any questions on that?
For encase and then module, we have to put like the single thing.
You don't, and Verilog always messes me up with that. You would think you would. In any reasonable programming language you would. And in any reasonable programming language you wouldn't have this semicolon here. But
It's very hard.
it's Verilog. I did not give y'all that one. I did give y'all this one. Okay, so now we're going to write the circuit that goes with this. And this is probably the first time you've seen a Verilog for a sequential circuit. Need to do something real quick. Okay, so whenever you see a Verilog that looks like this, you can be pretty sure that what this is going to be is some kind of register, and it's going to have as many flip-flops as it has in its for loop, where it's just telling you what's going on with the different flip-flops. So when we look at this, we see that it has parameter n equals 3, and we've got reg n minus 1 to 0 q. So that's the same as saying reg to 0 q, or that we have q2, q1, and q0. And we have output side 1, and we have integer k. This integer is going to be used for the for loop. Okay, then we have an always block, and it says always at the positive edge of the clock. So that means that this is going to go through at every positive edge of the clock. And when we start, k equals to 0. And it says if v, so if v equals 1, then k is 0. So if v equals 1, then q of 0 becomes equal to Q of 1. Else, so this means if V equals 0, then Q of 0 becomes equal to W, or exclusive or Q of 1. So just kind of writing that out. And that's for K equals 0. And then we'll add 1 to K. And so if K equals 1, K is still less than N minus 1. N was 3, so K is still less than 2. So when K is 1, we'll get the same thing will happen if V equals 1, Q of 1 will become equal to Q of 2. If V equals 0, Q of 1 will become equal to W exclusive or Q of 2. This little arrow right there, non-blocking, what that means is that it's not going to change any of the values until you get all the way out of the always block. So you don't have to worry about if you say A equals B and then C equals A, C is going to equal whatever A equaled at the very beginning. It doesn't change the values until you get to the very end. Yeah.
And I think your laptop monitor is blocking the corner.
It is.
That's good.
Okay. Okay. And now, no longer is K going to be less than N minus 1 because K is now 2, and 2 is not less than 2. So then the last thing it tells us is that Q of 2 becomes equal to side 0. And then we have that last assigned thing. Assign side 1 equal to Q0. Okay, so what I have learned by doing this is that I've got 3 flip-flops. So I know I'm going to have 3 flip-flops. I'll come back to that if y'all need that, but you might not need it after we draw it and you see what's going on. So, and we usually use D flip-flops. And if you get a question like this on the test and you're not sure what else to do, you can always look at the code and say, okay, well, I've got 3 flip-flops. I know I'm going to have D flip-flops. They're probably going to have a clock. You'll get some credit, right? And then if it's got an if in there, it's probably got a multiplexer. And I'll label this one 2, 1, and 0. And we had a decision to make for flip-flops 0 and 1. For 2 didn't enter into the for loop, so we didn't have a decision for it. So whenever you have an if statement, that's going to be a multiplexer, and the value of the multiplexer is going to go into the flip-flop. And now let's look at D0. We said if V equals 0, so V is our input into the multiplexer. If V equals 0, Q0 becomes equal to W exclusive or Q1. Okay, so this was if V equals 0. So it's going to go into the 0 of the multiplexer. and it equals the exclusive OR of Q1 and some variable named W it's got a shiny wire. And if V equaled 1, it just became equal to Q1. So if V equaled 1, it just became equal to Q1. And Q1 did the same thing. If V was 1, it became equal to Q1. Otherwise, it became equal to the exclusive OR of W and Q2. This has got to be almost a new record for my worst diagram ever. I've drawn some bad ones, but I don't know if it's ever been this bad. Okay, and then it says Q2 becomes equal to side 0. So I just have some other variable over here, side 0, that is going into Q2. And then the last thing, aside sine 1 to Q0, just means the output here is going to be side 1. I just couldn't let that stand. I had to, you know, make it at least somewhat legible. That should be the same thing. All right, so any questions? Yes.
So what was like the giveaway that it was going to use 3 flip-flops?
That the for loop went through 2 of them. It was the amount of Q's, and the Q kind of tells you. So Q is 3 bits wide, and so each Q is going to be a flip-flop. Okay, other questions?
And also, how in the code does it like differentiate differentiate between v equals 1 and v equals 0?
That's the multiplexer. And in the code, it has if v. So this is if v equals 1. And this is v equals 0.
It's the condition.
It's the condition.
I see.
Okay, other questions? All right, so if you want more of these to practice on, I have lots of examples from previous years. They tend to follow a similar pattern where you have to figure out if things are being shifted from one register to the other or loaded or something like that.